Okay, so we're back and we're ready to go over this problem further. I encourage you to perhaps try to do this by yourself ahead of me. So, uh, pause this video perhaps and then see, where it goes, or see if we get to the similar results. So now, let's take a look at it. Let me redraw this picture over here without all those details. So here's our circle, and let's put a bunch of positive charges in there, and let's say that's our center where we want to know the electric field. Let's call this our infinitesimal charge dq, and this is a small part of the half circumference dl, and we see there is our electric field, a small portion of it can be broken down into its x components and to its y components. Even though we already verified over here that the x components will cancel, meaning that we need only worry about the y components, we're gonna try to model both of them anyway, just for the sake of exercise. Now let's take a look at this little circle that we have, half a circle we have here. If we know this is a radius of r, right, and we can also recollect that for the small radius of r we have this infinitesimal circumference dl, therefore this covers a part of the circle d theta. So we can remember something maybe from a lower grade of school, the arc length formula. R theta is equal to our arc length s. So because we're looking at a small amount of our circumference under a small amount of angular displacement, we can say r d theta is equal to ds. Now we know what our radii is, so we can write this in terms of variables that we have here in our problem. So we call that r d theta is equal to dl. So that seems like a reasonable substitution we can make. So taking this for dl and recollecting that we previously defined this as our intensive property, and I don't really care right now, we can now go ahead and put 2 and 2 together, and we see that our intensive property can be redefined as q over pi r, which is equal to dq over r d theta. Okay, and what do you know? Lo and behold, we don't really need to worry about what our radii is here. We can cancel them off on both sides. So we see that we can make our intensive variable q over pi is equal to dq over d theta. And it makes sense. The bounds for theta is going to be pi. That's what we have when we're dealing with a semicircle. It goes from 0 to pi. And that's what our charged wire is in the shape of. Alright, now let's go ahead and fill in the variables to describe our electric field in the x and the y component. Alright, so we see over here that dex is going to equal to our de magnitude. And where does our angle actually pop up out of this? Well, for that we're going to have to look back at the figure a little bit more. So if we look at our figure here, what we see is, well, from here to here we see there's an angle of theta. Now if I superimpose an xy plane upon this, I see that this angle theta also shows up over here. And likewise, I can translate my y component over here without changing its size or magnitude. And now I have a right triangle hiding in here. So let's draw this right triangle out. So now here it's pretty simple. We see that the x component is adjacent to our angle, so we say that is cosine of theta. And likewise, we see that the y component is opposite our angle theta in this figure, so that is going to be this times sine of theta. And now we can go ahead and recall what dE was. We know that that is going to be k times q over r squared times cosine of theta now. Likewise, this will be k times q over r squared times sine of theta. Alright, I've already said the x component's not that important for us. They're all going to cancel. We verified that previously. So we're just going to focus on working with the y components. Alright, now let's deal with this y component. And I made a mistake, so please forgive me. Should have been dq. Okay, so now we're going to use our intensive property here to rewrite that. So I want to get rid of the dq. So one thing I can write is lambda d theta is equal to dq. And that's fine, but what about lambda? Well, I can still go further with this. Lambda is basically this, q over pi. So I can say q over pi times d theta is equal to dq. Alright, now I can go ahead and plug this into my equation I have over here. So now I'm going to see that dEy is equal to k times q over pi r squared sine theta d theta. And I know the bounds for theta here. Remember, it's a semicircle, so we're going from 0 to pi. So let's keep going with this, or actually we'll continue this in another video.